We have two types of mechanical waves. First kind is called transverse. The second kind is called longitudinal. This is a transverse wave. In a transverse wave, the wave particles don't travel with the wave. Rather, they travel perpendicular to the wave. If the wave is traveling to the right, then the particles within the wave are all traveling in their own little zone up and down, perpendicular to the motion of the wave. We say that the motion of those particles, each one of them is simple harmonic motion. There's the tie-in between simple harmonic motion and waves, right? Wave motion is motion, simple harmonic motion of individual particles within the wave. We labeled a number of things on this transverse wave, crests being the peaks or the bumps of the wave, trough being the valleys of the wave, or we could say the valley or the dip of the wave, the wavelength, the length of a wave, or the distance over which a wave repeats itself. I'm going to start right here, and I want you to tell me when to stop, when I've reached one complete wave length, when I've reached the distance over which the wave starts repeating itself. Tell me when to stop. Yell out loud. Right. That's one wavelength given by the symbol lambda, Greek letter lambda, L-A-M-B-D-A, the distance over which the wave repeats itself. Let's try another one right, start right here. Okay, tell me when to stop here. Yeah, good. We could do it from anywhere to some other spot as long as it's the distance over which the wave repeats itself. Finally, the amplitude, which is related, by the way, to what variable? The size of the amplitude, the height of the wave, is related to the what property of the wave? Yep. The energy of the wave, right? The more the amplitude, the more the energy. And it's not even linear, it's exponential, right? So if you double the amplitude of the wave, if you make the wave twice as high, then it ends up making the energy of the wave 4 times as high. So the amplitude, as measured from the equilibrium position, or that level spot in the middle, to the top of a crest, or from the equilibrium position to the bottom of a trough, either one. Just don't do this, okay? Just don't label it from the top of a crest to the bottom of a trough, because that's wrong. Okay, that would be twice the amplitude. Now, our other kind of wave is our longitudinal wave. We always picture a wave when we're asked to think about a wave. We always picture the transverse wave, because that's the water wave, right, that we typically see. But a longitudinal wave carries energy same way as a transverse wave carries energy, through vibration or simple harmonic motion of individual particles. But in this case, if the wave is traveling this way, the particles vibrate not perpendicular to the way the wave travels, but parallel to the way the wave travels. And they're in their own little zone, right? It's not like the particles are traveling from here way down to here. Okay, they're in their own little zone, going back and forth, back and forth, back and forth in simple harmonic motion, parallel to the way the wave travels. Now, we don't label a crest and a trough. We label a compression and rarefaction. The compression is the area where we have high density or high pressure, where it's squished together. Remember the Slinky demonstration? Okay, Reed, remember the Slinky demonstration? Yeah, I know you do, because I heard you talking about it before. Where the Slinky wave is scrunched together, right? That's the compression, and the area right behind it or in front of it would be the rarefaction. That would be where it's stretched out, where you have a lower density or lower pressure. If we had to label a wavelength here, well, let's do that. Let's label a wavelength here. Let's say we're starting right here. Can you tell me when to stop when I've reached one complete wave, or the distance over which the wave repeats itself? Tell me when to stop. You mean stop way back here, right? That's what you meant, right? Yeah, that's what I thought you meant. Yes. That's one complete. It's harder to label it on here, right? It's harder to visualize it on here because of the shape of it. But at the end, if we're going from the middle of a rarefaction to the middle of the next rarefaction, that's the distance over which the wave repeats itself. So that's one complete wavelength. Similarly, we could label this one from the middle of a compression to the middle of the next compression would also be one complete wavelength. Now, pretty hard to label the amplitude of this, but you can imagine the more it's compressed, the more it's stretched, the more energy is possessed by it, so therefore the higher the amplitude. It's just a little bit harder to see it on the wave itself. All right? Next, we talked about the speed of a wave. We said, as long as the wave doesn't change materials or medium that it's in, as long as it doesn't go from, let's say, air to glass. When light goes from air to glass, it changes speed, right? When water goes from warm water to cold water, it changes speed. But as long as it stays within the same medium, within air, or within cold water, or within whatever, then the speed doesn't change. It's a constant speed. And therefore, we can describe the speed of a wave by using this equation, as long as it stays within the same medium. But we can tailor that equation as well. We can make that equation unique to waves by replacing delta D with another distance, a specific distance, a distance over which the wave repeats itself, which we call the what? We just did this. The distance over which the wave repeats itself is the wavelength. So let's say V is equal to delta D, or V is equal to lambda, the distance over which the wave repeats itself, divided by time, specifically the time over which the wave repeats itself, which is nope, but you're close. Not the frequency. What's the inverse of the frequency equal to, Kyle? Yeah. So we could say V is equal to lambda over the period. Now, that's a valid equation, but we don't usually see it written like that. Usually we end up replacing T with 1 over F, which gives us an equation that looks like this, which looks kind of ugly, so we can simplify it. And when we do that, it ends up looking like this. V is equal to F times lambda. That's what we call the universal wave equation, and that's exactly the way that it appears on our data sheet. So, remember that when you're dealing with wave motion, as long as you're not changing media, as long as you're not going from one medium to another, from cold water to warm water, from air to glass, from water to air, as long as you're staying within the water or within the cold air or within the glass or whatever the case may be, then these two equations apply. V equals D over T and V is equal to F times lambda. Now, if we do change media, if we do go from air to glass, or we do go from cold water to warm water, or from water to air, then the speed will change. So will the wavelength change if we go from one medium to the other. But even if we go from one medium to the other, one variable, that's the frequency, doesn't change. Once a wave has been made, no matter what happens, the frequency isn't going to change. Okay, remember that. It rears its ugly head a little bit later on today in one of the questions that you're going to work on. You guys had a few questions that you were working on before the break, page 409. I want to take a look at, I want to take a look at question 2 and 3 on page 409. And if we have to, take a look at question number 1 as well. Anybody need number 1 going over, or are we good with 2 and 3? Good with 2 and 3? Okay, let's take a look at those now then. Number 2 says, a submarine sonar system sends a burst of sound with a frequency of 325 hertz. The sound wave bounces off an underwater rock face, returns to the submarine 8.5 seconds later. The wavelength is 4.7 meters. How far away is the rock face? This is how the submarine knows where to go, right? Like, you can't just look out. You don't have the captain of a submarine just looking out the windshield and saying, hey guys, there's a rock up there, turn right. Like, we have navigation equipment to help us, or to help the submarine know where it is, right? By sending sonar, by sending these sound waves, bouncing them off. It's kind of like a bat, right? How a bat sees. Okay, what do we got given to us in this question? Something's 325 hertz. What is that? Quick. It's frequency. So even if the wave changes media, even if it goes from cold water to warm water or something, doesn't matter, that frequency is going to stay the same. Never going to change. The sound wave bounces off an underwater rock face, returns to the submarine in 8.5 seconds. That's going to be time, right? Is that right? Seems to be. The wavelength of the sound is 4.71 meters. That's going to be lambda. That's not delta D, We're not talking about how far the wave has moved here. We're talking about what the length of a wave is, or the distance over which the wave repeats itself. What are we looking for here? What variable is it that we want to solve for? Brogan, what is it? What are we looking for? Yeah, yeah. Yeah, like what do we call that? How far away is the rock face? Yeah, it's the displacement. The displacement of the distance or the displacement of the wave, right? So what do you want to do? What do you want to do? Rachel, what do you want to start with here? Okay, let's find speed here by using probably f times lambda. Okay, that works. Right, how many times have we said this now? 1,000,000 times, right? Where, listen, you're not sure what you want to do, just do something. That's a valid equation. Let's do that. It's probably going to help us. If it doesn't, worst case scenario is, all right, we got to start again. 325 times 4.71 gives me a speed of let me try this again. 325 times 4.71 gives me a speed of 1,530.75, which, by the way, is very, very fast. About 4 or 5 times the speed of sound in air. Sound travels a lot faster through water than it does in air. Now what? I don't know. The only other thing that I know in this is what, Kyle? Yeah. V equals d over t. Solve for d here. I get v times t. I get 1530.75 times the time here of 8.50 seconds. And when we do that, we get the wrong answer. Well, we don't actually get the wrong answer. We're just not finished. What's wrong, or let's say it in a better way, what's incomplete about what we've just done? Brogan? Yeah. How come, Brogan? Yeah. We are given the time that it takes the wave to go there and back. What are we looking for? The distance that it takes the wave to go there. So we've just solved for the distance there and back. If we want to solve for the distance to the rock face, we're going to divide that by 2. And when we do, we get, presumably that's the answer that's in the book, 6.51 times 10 to the 3 meters. Now, what's the other way we could have handled that? Got the same answer, got the same correct answer. Yep. Yeah. You either got to take the time there and back, get the distance there and back, and then divide the distance by 2, or divide the time in 2 right off the top. And then when you solve for distance, that'll give you the distance there. In either case, you're going to get 6.51 times 10 to the 3. Is that okay? All right, let's take a look at number 3. So it says a fisherman anchors his dinghy in a lake 250 meters from the shore. The dinghy rises and falls 8 times per minute. Finds it takes the wave 3 minutes to reach the shore. How far apart are the wave crests? Don't make this harder than it has to be. Something here in number 3 is 250 meters. What is that? If we see meters, we typically think of a distance, right? A length. What is this? Is this the wavelength? Kyle, what is it? Yeah, it's the distance that the wave travels, or you could call it the displacement. Time is 3 minutes. We're going to convert that to seconds, though. We'll multiply by 60 and get 180 seconds. What are we looking for? How far apart of the wave crest? It's lambda, isn't it? What is this 8 times per minute? 8 cycles per minute. What's that? I know that you guys frequently have trouble with that variable. What variable is that, Braden? That's the frequency. Although we want to convert that to cycles per second, right? So cycles per minute. So let's divide that by 60. 8 divided by 60 gives me 0.133. Let's say V equals d over t. Speed is 1.3888 meters per second. And then let's say lambda is equal to V over F. $10.4. Get around that to 2 digits, I guess. 10 meters. How many people got both of those questions? Okay. Good. There's really only 2 equations, right? Like, try one. If it doesn't work, try the other one. A lot of times you got to do both, but say there's only 2 equations. Really, there is another one, I guess. Conceivably, you have to use that one. T is equal to 1 over F. Doesn't pop into these too often, though. All right, we're going to give you a little bit of time to kind of get your mind back into things here and work on some questions here. I want you to take a look at page 410, questions 1 to 9 on page 410, please. I want to take a look at 3 questions. Number 6, starting with number 6, says temperature changes in seawater affect the speed at which sound moves through it. A wave with a length of 2 meters traveling at a speed of 1,500 meters per second, which again, like I said earlier on, is about 4 or 5 times the speed of sound in air. Sound travels a lot faster through water than it does in air. Reaches a section of warm water and it speeds up even more. What do you think the wavelength is going to be in warm water? The way we want to tackle this is to treat kind of as 2 problems. Treat it as kind of 2 problems, right? We've got cold water, and then we've got warm water. Let's write down our givens for both. In cold water, we know that the length of the wavelength is 2.00 meters, and the speed of the wave is 1,500 meters per second. In the warm water, you can see that the speed changes to 1,550 meters per second. We're looking for the wavelength in the warm water. Clearly the speed changes. Clearly the wavelength changes when we go from one medium to another, from cold water to warm water. What doesn't change? Good. The frequency stays the same. So what I want to do in question number, or in the first part of it, is solve for the frequency. F is equal to V over lambda. We've got 1,500 meters per second divided by 2.00 gives me, what is that, 750 hertz. That means if the frequency in the first stage, the cold water was 750, then it's going to be 750 in the warm water as well. Lambda is going to be equal to V over F, 1,550 divided by 750. And I think we end up getting, I want to say it was 2.07. Is that right? Does that sound right? 2.07? Now, somebody asked me, could we just do a ratio with this? I'd rather you not do a ratio with this. It works, but I'd rather you not. Here's why. If you did a ratio with this, you'd get the right answer. But a lot of times what happens when we recognize something like that, we do a ratio, gives us the right answer. A lot of times it's a recognition kind of after the fact. We know what the answer is. We see, oh, a ratio would have gotten me that answer. When you're doing this question on a test or on an assignment, you don't know what the answer is. So you don't have the benefit of hindsight to be able to say, oh, all I got to do is do a ratio here. Now, if you just tried a ratio right off the top without knowing what the answer was, it would work here. But only because the relationship between V and F is a linear relationship. Sorry, between V and lambda is a linear relationship. If it wasn't a linear relationship, in other words, if it was v is equal to f times lambda squared, then a ratio wouldn't work. Or if it was v is equal to f times the square root of lambda, or v is equal to f over lambda, then the ratio thing wouldn't work. And clearly, you know that there's lots of equations that we do that have a squared in them, or a 1 over an inverse relationship in them. So I would suggest that you avoid, you lay off the ratios there, and just solve for it using the equations. Because the ratios sometimes will lead you astray. If it's a linear relationship, it's fine. But if it's not, then the ratio thing doesn't work. All right? How many people got 2.07 then? Good. Next question I want to look at was question number 8. When you generate a wave in a spring, what's the relationship between the frequency, the wavelength, and the amplitude? Let's do frequency and amplitude first. What's the relationship between frequency and amplitude? What is the amplitude of a wave related to? Yeah. It is the height, yeah, but what's it related to? What variable, what quantity determines how big or how high the wave is? In order to make it higher, you need more what? Energy, yeah. So the amplitude is related to the energy. How is the frequency of the wave related to that? It isn't. There is no relationship between frequency and amplitude. There is also no relationship between wavelength and amplitude. How long the wave is, or how many waves per second occur, don't have any bearing on how much energy the wave has. And the energy the wave has is essentially what tells us what the amplitude is. So there is no relationship between frequency and amplitude, wavelength and amplitude. What about frequency and wavelength? As the frequency goes up, the wavelength goes down. It's an inverse relationship. Right? F is equal to v over lambda. It's an inverse relationship. As one goes up, the other goes down. Finally, let's take a look at question number 9. Two tuning forks are generating sound waves at the frequency of 384 hertz. The waves from one tuning fork are generated in air where the sound travels at 350 meters per second. The other is underwater where the speed of sound is 1,500 meters per second. What's the wavelength for the sound in air and in water, and would you hear the same musical note? So A, we're going to say the frequency is 384. The speed of sound is 350. Solve for lambda. Equals f times lambda, or lambda is equal to v over f. 350 divided by 384 divided by 350. What does that equal, by the way? Is that something like 1.1? 1.10 meters, is that right? Isn't it 3? Yeah, it's 350 divided by 384. Yeah, that's why you guys were all looking at me like I have a hole in the head or something. 350 divided by 384. Thank you, Janae. 350 divided by 384 gives me 0.911. Is that right? How many people got that? Good. 0.911 meters. Good. Now the second one, we do exactly the same thing, right? Except that this time our speed is 1,500 meters per second. Gives me a wavelength of 3.91. We would expect a bigger wavelength given that we had a bigger speed. Let's see. Would you hear the same musical note underwater as you did in air? Who takes band here? Who's in band? No, but none of you guys? Seriously? I always get physics people in band. It's like physics and band seem to go together. if you've taken band in the past, you would know that the note that you hear is related to what? What property of a wave classifies the note that you hear? Pardon me? Yeah, it's the frequency. So each different note has a different frequency. All right, what do we know about frequency? Once a sound has been made, or once a wave has been made, the frequency. Okay, it could change the wavelength or the speed if it goes into a new medium, but the frequency of the wave doesn't change, right? So what would we hear here? If we have a frequency of 384 in both cases, would we have the same note or a different note? We'd have the same note. Differences in the second question, B, you just hear it a lot sooner. Okay, the note would travel to you about 4 times faster than it would in the first question, but you still hear the same thing.